we want to talk about estimators and specific properties of estimators. So to motivate that, what we want to know is we want to know the population mean, which is mu, or the population variance, which is sigma squared. Those are two statistics or parameters about the population that we care about. So we can put the equation for the mu is just the expected value of x. And if I have data of the entire population, this is just 1 over capital N summation of xi. And for sigma squared, this is just the expected value of x minus mu squared. And if I have data for the entire population, this is just 1 over n summation of xi minus mu squared. But the problem is, I don't have the entire population. I might only have a sample. And so I don't have all of the xi's for n, or for capital N. Furthermore, for the variance, I don't have all the observations for capital N, and I also don't have mu, because I don't have the population mean. And so because we don't have these population parameters, what we want to ask ourselves is, are there estimators from the sample that we can use that will be good estimates of the population parameter? So one thing we want to think about is, well, I could use is theta hat. Let's let theta hat equal x bar. Theta hat being the sample estimator. And the population parameter we care about is mu. So in the notes, we oftentimes see theta hat and theta, and that's just theta hat is a sample estimator, and theta is the population parameter we're trying to estimate. Now in the sample, we want our samples to be IID, independent and identically distributed. And so if I'm going to use x bar, I want to know, is x bar a good estimator for mu? Well, one of the properties we can look at is it unbiased? The definition for bias is the bias of theta hat is equal to the expected value of theta hat minus the population parameter. And this is true when the expected value of theta hat is equal to theta. So if I take the expected value of the estimator, I should get the population parameter. So that is one measure of if it's good. So let's go ahead and look to see, is x bar a good estimator, or rather an unbiased estimator of mu? So I would take the expected value of x bar, and this is equal to, now I'm going to work through some math here. This is the expected value of 1 over n summation of xi. I've just broken apart x bar into its individual parts. I can pull out the 1 over n, the expected value of the summation of xi. Now, a party trick we've learned is that estimator, the expected value is a linear operator. So this is equal to 1 over n, the summation of the expected value of xi. Well, what do I expect xi to be? Well, that comes up here from our definition, is I expect xi to be mu. And that's because of IID. If we are identically distributed, then each xi pole I would expect to be mu. So this is equal to 1 over n summation of mu. Notice mu does not have any I subscript. And so then I get the summation of mu, which is going to be n times mu. These n's cancel, and so I'm left with mu. Or in other words, the expected value of x bar is equal to mu. And this is our final answer, which shows then that the bias of x bar is equal to the expected value of x bar minus mu. And we showed that the expected value of x bar is equal to mu, so mu minus mu is 0. So we showed that x bar is an unbiased estimator for the population mean, mu. So that's really good. Another way to show if something is a good estimator, we'll write it over here, is it consistent? So this is where we have a definition of consistent is going to be as n gets large, then the bias of theta hat is going to go to 0. And we need both of these. The variance of theta hat goes to 0. So the question we want to ask, is x bar a consistent estimator of mu? Well, we showed earlier that the bias of not theta hat, but of x bar is equal to the expected value of x bar minus mu. And this was equal to mu minus mu, which is 0. And so it's not a function of n. So as n goes to infinity, we have a check mark for this first condition. Now we need to show that the variance of x bar as n goes to infinity is equal to 0. So let's see what the variance of x bar looks like. Well, this is equal to the variance of 1 over n summation of xi. So I can pull out that 1 over n, but I have to square it. So 1 over n squared, the variance of the summation of xi. So I can break apart this as, I can rewrite this as 1 over n squared times the variance of x1 plus x2 plus x3 plus xn. Now, what we cannot do without certain assumptions is this does not equal the variance of x1 plus the variance of x2 plus variance of xn automatically, because we would have this plus 2 times the covariance of x1, x2, and all the other combinations. So we would have this covariance term that's really important. However, if we have IID, then what the first I says is that they are independent. And if x1 and x2 are independent, then this means that the covariance is equal to 0. So through independence, we can write this next step as equal to 1 over n squared times the variance of x1 plus the variance of x2 plus the variance of xn. And that's through independence. Well, what is the variance of x1? Well, the variance of x1 is simply sigma squared. So we'll get sigma squared added together n times, and so this is equal to 1 over n squared times n times sigma squared, and so the variance of x bar is equal to 1 over n sigma squared. And we want to ask is what happens as n goes to infinity? Then this implies that 1 over infinity sigma squared is equal to 0. So now we can add a second check mark here to show that X bar is a consistent estimator of mu because it was the bias is equal to 0 and the variance of X bar is equal to 0 as n goes to infinity. So we can show here that an estimator is good by looking if it's unbiased and by looking if it's consistent. And in this case, we can say that X bar is both an unbiased and a consistent estimator of mu.